Sometimes researchers will take the logs of dollar-valued variables, which we've done here. Now the mean of the employment population ratio is still 50.23, but the mean of our independent variable, natural log x1, is only 5.44 log dollars. The mean of x1 was $250. The standard deviation of the employment population ratio of low-income single mothers is still 8.886. The standard deviation of log x1 is 0.41. The covariance between the employment population ratio and natural log x1 is only 0.1. The reason why researchers do this is because, one, the dependent variable y is measured in percentages. When the dependent variable y is measured in percentages, like it is here, the estimated slope coefficient becomes kind of like an elasticity when we take the natural log of a dollar-valued variable. The slope is calculated the same exact way as it was before, only this time we're taking the covariance of the new variable natural log x and y. We're dividing that by the variance of the new variable natural log x. We plug in the numbers. The covariance of natural log x and y is 0.1. The standard deviation of the new variable natural log x is equal to 0.41. Therefore, the variance of the new variable natural log x1 is the square of the standard deviation. The slope coefficient is equal to 0.6087. The new intercept is computed the same way as it was before, only this time we're using the mean of the new variable natural log x. The mean of y is 50.23. The estimated slope coefficient is 0.6087. The mean of the new variable natural log x is 5.44. The intercept is 46.9192. And we interpret this as what y would be on average if x equal 1. The log of x would be equal to 0. 0 times the slope is 0, hence the employment population ratio would be equal to 46.9% if the state sets its benefit level equal to $1. The new predicted equation is y hat equals 46.9192 plus 0.6026 times the new variable natural log x1. Here's our new predicted equation with the transformed independent variable. This is a sample mean of the transformed variable natural log x. This is a sample mean of our dependent variable of the employment population ratio. So we've done this before. To compute y hat, the first predicted value of y, we plug the log of the first observed value of x1, which is 4.71. Remember, the units here are logged dollars. When we plug this number into this new transformed variable, we take 46.9192 plus 0.6087 times these log dollars, 4.71, and we get 49.78. Now, we want to compute the total variation in the transformed variable. So we have to compute the first deviation from the mean of the transformed variable and then square it. So what we do here is we take 4.71 and subtract from it 5.44. We square that difference and we get 0.543. Now we've already done this in a previous slide. This is just the first observation of y, 52.35, minus its mean of 50.23, and then we square that difference. We've also done this as well. This number here is computed by taking y, the first observed value of y, and subtracting off its predicted value, 49.78. The result is the estimated error, which we also call the residual. We square that number, we get 6.57. The final number in this last column is found by taking the first predicted value of y and subtracting off the sample mean. So we take 49.78, subtract off 50.23, we square that difference and we get 0.20. The second predicted value is equal to 50.84. To get this number, we take 46.9192 plus 0.6087 times the second observed value of our transformed variable, 6.43. The second squared deviation from the transformed variable's sample mean is found by taking 6.43 and subtracting off 5.44 and then squaring that difference. We've already computed these three numbers in a previous slide. The third predicted value of y is found by substituting 5.46 into the equation here. So we have 46.9192 plus 0.6087 times 5.46, which equals 50.24. To get the third squared deviation from our transformed independent variable, we take 5.46, subtract out 5.44, which is really small, and square that difference. Now it's not actually equal to 0. 5.46 minus 5.44 is 0.02. 0.02 squared is actually 0.0004. But we're only using three significant digits. Now we've again computed these three numbers in a previous slide. Now the rest of the y-hats are estimated in a similar way, along with the rest of the squared deviations from the transformed variable's sample mean. Now the total variation in the transformed independent variable is found by summing all 100 of these numbers. So the total variation in the transformed independent variable is only 16.28. Now if I divide this by 99, I get the variance of the transformed independent variable. The total variation in y is no different than it was when we did this earlier. The total sum of squares is still equal to 7,764.76. Now because we have a new model, the y-hats are all different, the sum of squares due to error is going to be different. In this example, however, the sum of squares error is surprisingly really close to what it was before. The sum of squares due to regression is the sum of this final column. To test for significance at the 5% level in our re-specified model, we recompute the t-stat, which involves recomputing several statistics, which regression software packages will compute for us. For instructional purposes, we recompute the new set below. The mean squared error, or the S-square, is equal to the sum of squares error divided by n minus 2. The sum of squares error for our re-specified model is slightly higher at 7,758.73. The degrees of freedom are no different because we still have a sample size of 100 and we estimated two parameters, the slope and the intercept. So the new mean squared error is equal to 79.17. The standard error of the estimate looks exactly the same as it was before, but it's not. We take the square root of 79.17 and we get the standard error of the estimate equal to 8.898. The standard error of the estimated slope coefficient is equal to the standard error of the estimate divided by the square root of the total variation in the transformed independent variable. 8.898 is the standard error of the estimate. 16.28 is the total variation in the transformed variable. Therefore, the new standard error of the slope coefficient, B1, is equal to 2.2055. The t-stat is equal to the estimated slope coefficient divided by its standard error. The estimated slope coefficient is equal to 0.6087. The standard error of the estimate is equal to 2.2055. Therefore, the new t-stat is 0.2760. The alpha level, or the significance level, is 0.05. We have a two-tailed test, so we divide alpha by 2 to get 0.025. The degrees of freedom haven't changed because we still have a sample of 100. So the degrees of freedom are 98. The upper T critical value is in column 0.025 and row 98 of the T distribution table. Therefore, the upper critical value is still 1.984. The lower critical value is still negative 1.984. And since the T-stat is in between these two values, statistically, the estimated B1, 0.6087, is no different than 0. Hence, we cannot reject the null hypothesis that the true slope coefficient, beta 1, is equal to 0. If estimated coefficient B1 was statistically significant, we'd interpret its value as follows. Suppose we want to know what happens to the employment population ratio of low-income single mothers if a state decides to increase its welfare payment by 10%. When we use a log dollar-valued independent variable, we have to do the following first before we interpret the coefficient. In 1994, the average TANF benefit check for a family of 3 was $266. A 10% increase in that average TANF benefit check is $292. How we find that is by taking 10% of this, which is 26.6, and adding that 26.6 to 266. When you add those together, you get about $292. So what we're doing here is we're essentially computing what y hat is when x is $292, and then we're also doing the same thing when x is $266. We take that difference, y hat when x is $292 minus y hat when x is $266, we get 46.9192 plus 0.6087 times the natural log of 292 minus 46.9192 minus 0.6087 times the natural log of 266. Simplification means the intercept is gone because 46.9192 minus 46.9192 is 0. So what we're left with is this part of the equation and that part of the equation. Here and here. Factoring the 0.6087 yields this equation. We factored out the 0.6087. So now we have the difference in these log values. We use a rule of logarithms. The difference in logarithms is equal to the log of the ratio of the numbers. Now 292 divided by 266 is 1.1. Once you understand that, anytime you've estimated a regression equation with a logged dollar value, the way you go about interpreting the coefficient is you write delta y hat equal to the estimated slope coefficient times the natural log of 1.10. And when we use a calculator, we plug in 0.6087 times the natural log of 1.10, we get 0.058. Now the interpretation of this number is increasing monthly benefit levels for a family of 3 by 10% would result in a 0.058 percentage point increase in the average employment population ratio of low-income single mothers. If I was interested in a 20% increase in the benefit level, I would have plugged in 1.20 and I would have got a different number here. Since estimated coefficient B1 was statistically insignificant, we interpret it as follows. Increasing monthly benefit levels for a family of 3 has no effect on the employment population ratio of low-income single mothers because B1 statistically was no different than 0. Our theory suggests that this estimate has the wrong sign and is biased towards 0. This bias is called omitted variable bias, and that's what you run into in simple regression.